Welcome to our discussion of research in psychology. How do we think critically about our social and behavioral world? How do we explore problems? How do we set up experiments and analyze correlations? So you can see we can break this down into some general categories. First of all, how do we ask questions? This will tie into theories and hypotheses, how they are different and why we need to be clear about why they are different. How do we define a variable? What is a variable? How do we use variables to measure constructs that may sort of be difficult to find actual information for? Variables are very important and imperfect, as we'll find out. And then finally, how do we actually conduct the research? What are some key terms and concepts that we need to know? And getting to this central question, why is it so technical? Why do I need to know all these maybe picky seeming terms, and why does it take so long to get the answers we really want? Why in many cases don't we get that answer with one study? So we'll address these and more issues as we move through today's discussion. But first, we'll present our key quote to give us some background on the issue. P.T. Barnum, circus performer, businessman, showman. Maybe some of you have heard of the Barnum effect, where related to this, but also the idea that there's a sucker in every crowd, when Barnum is talking about giving a little something to everybody, this is him saying that people are very susceptible to information that is in reality very general, but that we like to believe is specific to us. So for example, if I shake someone's hand and I say, wow, you've got a very aggressive attitude and I like it. That's a very general statement, but the person receiving that information is much more likely to believe it than they should. What does this relate to experiments and psychological research? Well, it means that we are not as skeptical about information as we should. And that leads into why do we spend so much time and effort and money developing these studies? Because it's a way to control for and protect us against our natural instincts to be more believable and more gullible in some ways, to be frank, than we should. Here is our key statistic. Basically, 13 to 41% of people who commit suicide do not meet the diagnostic criteria or requirements to be diagnosed with major depression. There are 2 points I wanted to illustrate with this. First of all, we can see this is quite a wide window. Which is the number? Is it closer to 13? Is it 41%? It makes a big difference where the true number falls. The problem is we have to accept error in our numbers. We want exact, round, perfect numbers, and unfortunately we just don't have those in many cases. What good research will do, and future research building on past research, will help perhaps to shrink this margin of error as well. The other point I'd like to illustrate is that when we're talking about a finding like this, we want to think, what is it? Is it a correlational data? Is it experimental data? Hopefully we'll get better at piercing through what this actually is. When I read this, I see 2 variables. One is committing suicide or not. You can also look at intentions to commit suicide perhaps, and also diagnosis of major depression. So diagnosed or not, commit suicide or not. Those 2 variables are actually correlated, meaning those who commit suicide is related to your diagnosis of major depression. Now, if I had to guess before knowing the statistic, I would say that they're very highly correlated. Those who commit suicide are very likely to be diagnosed with major depression. That still is the case. More than half of the people who commit suicide do have major depression, but this number also goes to show us that maybe that correlation is not as strong or as high of magnitude as we might have guessed beforehand. Another example of why do we need to do research? Well, an issue is that many of the things we take for granted as truth end up not having the research support that we almost certainly would have expected there to be. One example would be the idea that fingerprints are sort of like snowflakes in that no 2 are exactly alike. Well, Let's see how fingerprints are used in court settings and see if there's a research basis for using them. What these researchers found in a review of the evidence, this is a Delbert procedure, this is not for the exam, of course, but basically it is a legal procedure to introduce evidence. And once it gets introduced to the court, it can be used as evidence to make decisions about whether people are guilty or not. We find that when they analyze this evidence, they conclude that the kinds of experiments that would establish the validity and standards about fingerprint use have not been performed. Uh-oh, that's sort of a scary thought. What this means is that in many cases, legal as well, the standard of evidence to decide that scientific information is useful or real is often much lower than the psychological or basic academic research standards. So that again shows that we are taking a very skeptical mindset. We have a high standard to meet before we say that we think some effect is real. And then even beyond that, as we'll cover a few times, it's not just whether it's real, whether it's there or not. Once we've established that, we also want to know whether it's big or not. Let's start with a quick true-false. Human intuition is not mostly accurate and largely free. There's a big pop psychology movement to say, trust your gut, trust your intuition. We are more accurate than we were led to believe. This is false. The only times I would really put a lot of faith in human intuition is for people who have a lot of experience in a very specific situation. And once they try to apply that intuition outside that situation, then they fall into this phenomenon. They believe they know it, but their intuition is probably not very useful. Psychology does strive to be objective and unbiased. The problem is that, of course, people are doing the research, and there are a lot of ways that the system could be gamed if we didn't have all these protections, if it didn't take so long, so if there wasn't this review process to publish research information. This is the big one that I want you to be able to understand by the end of the class today. This does not prove causation. This is a correlational finding. Children who watch violent TV also is related to violent action, but just because two variables are related or correlated, that does not mean that we can say that one causes the other. If we want to imply causation, we have to do an experiment, as we'll find out. Think about this. Do we tend to overestimate or underestimate the number of people who share attitudes and values? In most circumstances, not all, but most, this is true. I think the effect is also amplified lately. So for example, if we are reading a story and check the comments section, we may have been drawn to the story because we are interested in that topic. And then we find out that in the comments section, lots of other people were drawn to that story because they were also interested. Just the fact that we see these dozens or hundreds of people commenting, we might then believe that there's a lot more interest in this topic than we thought before, when in fact it's mostly a selection issue and we are just part of people drawn to that topic, and then we use that to overestimate the base rate of all the people around us who believe that. So again, we have to build in corrections so we don't use this as a bias in interpreting our research. This is often a colloquial phrase, familiarity brings contempt. This is false. In most cases, we actually like things that we are familiar with, and we find comfort in being around people and situations that we understand and are familiar with. And I just like to throw this myth out there. Being in stressful situations, especially being in charge, causes ulcers. There's no evidence for this claim. In fact, being in charge of a situation actually implies some sort of control, which helps to reduce stress, in fact. When we're talking research, we don't want to have to think like Lucy. But in fact, that's what our research is actually doing. So we never prove something to absolutely be true. Instead, the research logic goes, we provide so much evidence for something that it is so unlikely that it's not true. But that also opens the door that maybe there are flaws in our research, maybe there are flaws in our sample, that in fact, even though most of the evidence points that way, it's still possible that that is not true. Also, there's a danger in just looking at isolated statistics by themselves. This goes back to the issue of, yes, we want to know if something's real, but then we want to compare it to other similar things to find out, is it large in magnitude? How important is it relative to other similar findings? So for example, if you're not afraid after seeing this about getting struck by lightning, and then you decide to go out in a rainstorm, driving around to watch the lightning, then you've engaged in a risky behavior that you wouldn't have if you didn't know the statistic. So let's get into some of the terminology. First of all, we have theories. These are general ideas or concepts that explain how things go together, how the world works. So a common phrase would be that misery loves company. People who are in bad moods want to seek social interaction. Then the hypothesis is just a small test. So the theory is the big thing. The hypothesis is just a nibble at part of that theory. And any good theory should be able to generate lots of different hypotheses. Now, take our misery loves company example, and then we clearly do two things. We say our variables more specifically, placing people in negative moods, and then seeking social interaction. Those are our two variables. And then we say, how are they related to each other? We'll be more likely to seek social interaction. And think about our world, right? Lots of shows. Ancient Aliens comes to mind. Conspiracy theories that we see in the news and pop culture. Theories are great. Theories are fun. But the hard work really comes in to generating these testable hypotheses. And so we see things like evolution may be just a theory. Well, yes, evolution is just a theory, just like any other conspiracy theory. The key difference is that evolution has been subjected to tests of many hundreds, probably thousands of different hypotheses, and most of them have supported parts or much of the evolutionary theory. So that's the difference. The difference is in the work, is in the data, but it can all start with just a simple theory. Quick test to see how we're doing. Remember, a valid hypothesis will clearly state the two variables and how they work together. So a hypothesis will not say what has happened in the past. It won't be wishy-washy and say may, but instead will say which way you predict these variables will relate. Now, in the big picture, we're talking about individual studies as they fit into the whole panoply of all the studies of a similar topic. So we start with a theory. We generate a specific hypothesis or two. We test it. We get the data. We think about it. And then we decide if we need to refine our theory or not. And then that leads to this reciprocating process in which maybe you develop a new hypothesis, or maybe you try to test that hypothesis with a different sample or in a different context. And then once you've replicated generally that initial theory 5 times, 20 times, and it can take years to get there, that's when we have strong evidence and a strong support for how we think the world works. When we're doing research, we have to really keep in mind the issue of populations and samples, particularly in psychology, since we're working with actual people to figure out how they think and how they behave. So the population is all the people who the study's goal is to explain. So for example, with elections, the population would be every eligible voter. With a drug trial, this would be anybody who could be benefited by the drug. So if we're working for an Alzheimer's drug that reduces memory impairment, the population for that would be all Alzheimer's patients. Now, of course, with most populations, we can't get the entire population. So for example, with the Alzheimer's drug, we can't get everybody with Alzheimer's in the United States. We don't have the money or the time to do that. So what we have to do is make a compromise, and that compromise is picking out a sample. So of course, with any election, not everybody who can vote does. The sample are the people who do vote. Then we have to decide how representative, and this is a key word to know, how representative of that population is the sample that you get. Now, of course, with elections, what's interesting is that for many states and many districts, and the national average on whole, if everybody who's eligible to vote does vote, then Democrats win in many cases. But of course, that doesn't happen many times because you don't have perfectly representative samples. You have things such as gerrymandering or other reasons why various demographics or parties don't turn out. So of course, what we'd like, especially for research, we'll move away from politics, is random samples, meaning that everybody in the population has a random chance of being drawn. That means we're not selecting more people who are older or younger or more people who are male or female. If we pick them out random, chances are those factors will even out. The problem is random samples are very tough to get. And in some cases, we may have data showing us that we're not getting random samples, and you might have to do what's called a stratified sample. If you are not getting a balanced, for example, demographic sample, you might have to make sure to reach out to go for underrepresented groups. So I'll go to this hiring job applicants example. Let's say you have 20 job openings. You post the job, you get your applicants, you interview them, you hire your 20, and then you find that you've hired 20 white males. Is that a problem? Well, it doesn't look great, but if your surrounding population is almost all white male, well, you've got a representative sample. In most cases, that's not going to be true, and so you may then have to go and say, okay, we are going to get a sample and use job posting techniques that are more likely to affect underrepresented groups, and you're not going to close the application process until you've hit 25, 40%, whatever number you want to choose of the minority applicants. And of course, you're not saying you have to hire a certain quota. That's not how affirmative action works. What it's saying is that you have to have a representative sample from the surrounding population. Otherwise, you open yourself up to potential litigation. A more simple example would be, let's say you want to know the ratio of red marbles to blue marbles in the big jar, but you don't want to count all the individual marbles. So what you do is you take a sample of the population, a smaller subset, hopefully it's random, you just dump them out, and doing a simple thought experiment, think about which is better, a larger sample or a smaller sample, 100 marbles or 20 marbles. Everything else being equal, the larger sample will be more representative. Of course, when doing actual research, maybe you'd like to have a sample of 10,000 people, but practically you only have the time and money to get 300. So you're making a compromise, and when we evaluate a study, we have to use that information when we're thinking critically about it. We have a couple more related concepts that we have to discuss. One would be the notion of replication. As we talked about before, if there's one study that says drinking soda once a day leads to cancer, is that going to be enough for me to change my behavior? Probably not. I would want to know, does that hold up across different samples? And often studies don't replicate. Sometimes the studies that try to replicate the initial studies that make the headlines are much better technically set up, and the better study gives you a better estimate. But sometimes studies have different samples. Sometimes studies measure variables slightly differently, and those results don't translate exactly. That's not a problem. It just means that we don't want to base important life decisions about one study in most cases. Sometimes you have studies that use national data and have tens or hundreds of thousands of people, and that one study is important enough and representative enough. But most studies that you see, you'd want to see replication before making life changes after having seen it. There's also the issue of generalizability. Do the results of one study generalize from the sample in that study to the larger population? And unfortunately, the headlines that we see often don't talk about this issue of generalizability. We have to think about them critically. We actually have to try and read parts of the study or dig deeper. And of course, the same pattern holds up. Larger samples do tend to be more generalizable. So in a vacuum, larger samples are almost always better. Now we're going to talk about some different research methods. We have 3 basic kinds. I will put this table up again after we've covered each of them. Basically, descriptive research is basically observing and recording, letting it play out, and making observations. We have correlational research. Here now we are putting numbers to variables. And then finally we have experimental research. We're not just putting numbers to variables that we've measured. Now we are introducing a lot of control over how those variables are measured. We are manipulating or controlling what some people get and what other people get, making sure that that's the only reason those 2 groups are different. So then we can infer that since one group took one drug, the real drug, another group took a fake drug, they all believed they were getting a real one. That manipulation can then lead us to infer that the real drug tends to cause different health effects, for example. So we'll dig more into all of these coming up. First, we have descriptive research. This is fairly straightforward. We have naturalistic observation. This is similar to people watching. So we have a picture of people at Walmart. You can go to Walmart and observe why people act and dress the way they do. You also have Jane Goodall here, who did famous naturalistic observation with chimps in the Gombe Preserve in Africa. She would spend many years of her life ingrained into these chimp societies and would see aspects of social behavior and dominance and pro-social behavior that no one else had seen. So it is very valuable, but it's not numerical. There's one other type of descriptive research called a case study. So we have Sigmund Freud, who did very strong case studies. So he studied his small group of people in depth over the course of years. So he really understood them well. That's the benefit. The problem is that you limit your generalization with case studies. So Freud's problem was that he did case studies with a sample of mostly rich white women and then used the results from that limited sample to try and generalize to all of humans. That was a problem. We also have Oliver Sacks. You may have heard of him. Recently passed away, but he did a lot of case studies with people with very bizarre and in some cases unique neurological disorders. We'll cover more of Oliver Sacks later in the semester. Let's talk about correlations. Basically, the name is a very good representation of what it is, a co, meaning 2 variables and the relationship between them. Then we have the actual statistic, which is the correlation coefficient. It can only be between -1 and +1. What's great about this is not only does it show whether there's a relationship, but how close that number is to -1 or +1 shows us how strong that relation is. It is great for prediction, which means that if I found in a sample that those who smoke 10 cigarettes every day have an increased rate of cancer, lung cancer specifically, I know that since that sample showed it, if I smoke 10 cigarettes a day, I'm going to increase my risk for lung cancer. Of course, I want to know, are the people in that sample, the study, similar to me? Is it people of similar socioeconomic status, people of similar demographics as me? But what the correlation does allow is if you know that 2 variables are related in one sample, then if I know that another person's value on a variable, I can predict their value on the other variable. Although we have to be careful because it doesn't explain why. It doesn't say that one variable causes the other. So continuing with the smoking example, we see that you can't do a study of randomly assigning some people to smoke a pack a day, other people to not, and then follow them 20, 30 years later, and then find out whether they have cancer or not. It's not ethical, it's not practical. Global warming is another example. Wouldn't it be great if we could do an experiment? We have one Earth that is nice and pristine and not polluted, the other Earth that we pump full of greenhouse gases, and if that one heats up, then we can say that it does look like greenhouse gases cause global warming. Of course, that's not practical. Now, what this means is just because we have a lot of correlational evidence, we can't definitively say that one causes the other. We also shouldn't put our head in the sand and disregard what most of that evidence seems to lean toward. So I think with global warming, climate change, there's been so much evidence now that, of course, we can't say greenhouse gases causes global warming. We should say that the evidence is so convincing that it probably does. That if we want to be careful and not risk serious problems for our environment, the research seems to show that some action would be warranted here. And once again, the two-step process of first deciding whether an effect is real. Is global warming real? Probably. The next step, and I think what we should be debating now, is how big is the effect, right? How much change are we going to see in what time window? And I think that's the argument that we should be having rather than whether it's real or not. So just a little funny example here. Basically, correlation does not imply causation, and you'll see this in any intro psych text. Again, it's kind of weird to think like that all the time, but if you're thinking like a psychologist, we are very precise in how we describe what we know and what we don't know. Now, it's important to understand how correlations work. First, you have a perfect positive when all the dots are on one line, and that means this is perfect prediction. You know that as this variable goes up, the other variable is also high. Low with low, that's the dot with these two variables. High on this variable is also high on this variable. If there's no relationship, on the other hand, we have a cloud with no clear line in there. Perfect negative is also perfect, meaning that's as strong of a correlation as you can get. This is equally strong as this one, but the way the variables relate is different. So in this case, a low value on this x variable correlates with a high value on this y-axis. It also means with a perfect negative correlation, if I know that I'm high on this x variable, I predict that I would be low on this y variable. Let's look at some real variables. Here we have maybe a basketball example. We have height and arm span, and we see that they are not perfectly correlated, right? They are pretty strongly correlated. If there's a clear pattern where that line would go, there's definitely a correlation there, but we have some outliers. So here's someone who has a huge wingspan who is shorter than we would predict based on that wingspan. On the other hand, here we have someone who is much taller compared to their average wingspan. And I think what we're finding out in the NBA especially is that before we thought that height was the biggest variable for predicting success, especially on defense. But now with the modern NBA, I think we're finding out that the larger wingspan is the better predictor for success, especially on defense. Here we see another strong correlation. Here we see husband's age is positively correlated with the wife's age. The older the husband age, the older we would predict their wife to be. But of course, we have some outliers, right? So this is maybe a cougar, so an older woman married to a younger man. And the opposite would be maybe here a trophy wife, an older man married to a woman much younger than we would predict given his age. There's all sorts of correlations. Correlations are relatively easy to measure and compute. They're all over the place. They're not tough to get. So here's a natural example. Now this correlation is negative, meaning that as the elevation goes up, the mean annual temperature goes down. And that can be read the opposite way. As the elevation goes down, the mean annual temperature goes up. Most correlations, on the other hand, especially in psychology, because we have so much more error, they look like blobs, and it's not obvious to tell if there is a correlation or not in here. So we see here age and cholesterol levels. We need to actually calculate the correlation to see if there's one here. Now, what we can say for sure is that this is not going to be a high correlation. It's not going to be a positive or negative correlation of 0.8, for example. If there is a correlation here, it's probably something closer to maybe 0.2 on the plus or minus side. We also have what's called the third variable problem. So for example, two variables are correlated. One could cause the other, or it could be that the order is reversed. Or oftentimes, more commonly, something else causes both of them. So for example, we have the common finding that sales of ice cream are correlated with murders. So does something about eating ice cream cause people to become murderous? Not really. The more important variable is probably the heat, whether it's summer out or not. And heat can raise anxiety or agitation, and that causes both, or it's related to, I shouldn't say cause, related to ice cream consumption, heat, we want to eat more ice cream, and heat causing violent acts. The more you smoke, the less you are expected to live. This is an example of as one goes up, the other goes down, a negative correlation. Which correlation would be best for prediction? The answer is the one that is the furthest away from zero. And of course, that is the one that's the biggest. Now, if we change this sign to a negative, the answer would still be the same. It would still be, compared to these answers, the furthest from zero and would enable the best prediction. Although, of course, with a positive, we say that as self-esteem goes up, body weight goes up. If this is a negative correlation, as self-esteem goes up, body weight goes down. And these are just made-up variables. So don't get too caught up in trying to think about the variables. Just try to interpret the correlation. ACT suggests that someone will do well in the future. Here we are in the prediction game. And again, correlations are great for prediction. We wouldn't say, however, that Cody's ACT score will cause him to do well in college. Let's move on into the next topic, the final type of research, and we're dealing with experiments. And here's where we really want to tease out cause and effects relationships. And of course, it's not just crazy mad scientists that do experiments. It's very normal looking researchers all over the globe. So unlike correlation, we just measure two variables as they happen naturally. Experiments, we manipulate or control a variable. Simplest example, if these get confusing, is to go back to a drug trial. Here we have the example of Clever Hans, the horse that looked like it could count. What do you know? Once we control or manipulate whether the owner and trainer is in the room or not, when the trainer disappears, Clever Hans appeared to lose his ability to count. So the classic example for a drug trial would be, does a drug affect a health outcome? So we have some key experimental strategies. One would be the idea of an experimental condition versus a control condition. As we'll find out in a little bit, it's not enough to know that someone improved after getting therapy or after taking a drug. We want to know whether they improved more than people in a control condition who thought they might be getting the real thing but didn't get the real thing. We'll find out in the next slide that this is controlling for the placebo effect. Most of the time, when we do something in our lives, whether we're going to school, whether we get a new job, whether we learn a new language, whether we marry someone, we think that that action is going to benefit us in some way. But sometimes our expectations don't match what's actually happening. And that's what we have to control for by doing experiments. So control conditions will get, people in the control condition will get a placebo, and the people in the experimental condition will get the real thing. And the trick is that neither of the people in these conditions know whether they're getting the real or the fake. It's easy in crop science. You just give the real fertilizer compared to no fertilizer and see if the yield's different by the end of the growing season, right? We talk about the Zimbardo prison study in which normal college students were recruited to be either prison guards or prisoners. The problem with this was that the person who did the study, Phil Zimbardo, made himself the prison warden. So in doing that, he made himself biased toward interpreting the results. Finally, another classic experiment that we'll talk about too is, does violent role model cause violent behavior? And what we found was that kids who watched this violent role model beating up this doll and using weapons against it, kids who saw that violent role model video when put in that room tended to act much more violently than the kids who did not see the violent role model. So once again, clear manipulation, which kid sees the violent role model video and which kids don't. We've controlled it. There's a couple more important things to consider. The double-blind procedure. In this case, neither the subjects nor the researchers know who's in the experimental versus the control condition. Of course, researchers are human. Think about a physician who prescribes a new experimental drug to his patients. He wants to see those patients do better, and maybe he wants to get some kickbacks for selling drugs. We don't know, right? If that physician knows who is getting the real drug, they might be inclined to change their views, to actually believe that the people getting the real drug are doing better than those aren't. So to control for that potential bias, the best research, especially in medicine, will do a double-blind procedure. And of course, all this is to control for what we know as the placebo effect. Basically, when people have something happening to them, or when they make a choice to do something, oftentimes they believe that it's going to help them, and they're biased in really interpreting what's happening. So of course, anything that says it is anti-aging, or things that say fad diets, infomercials, herbal supplements, most of that has very poor research showing that it really affects anything. But still, due to the placebo effect, people are convinced that it works on them. So of course, my example, why is Mountain Dew here? I need to have some every morning, but I'm probably used to that. I'm sort of conditioned to that. Maybe I'm having a placebo effect. Maybe that caffeine doesn't really affect me, but I feel it does, and so I keep doing it. Finally, we need to break down the causal order of the variables we're thinking about in an experiment. So first of all, we have the IV. This is what we manipulate, and this is what we think does the causing. And of course, the IV causes a change in the DV. The dependent variable is dependent on the independent variable manipulation. So for example, let's go back to the drug trial. Your memory is dependent on which Alzheimer's drug you got, the placebo sugar pill or the real Alzheimer's memory drug. Now, of course, in a good experiment, we clearly define our IV and DV. And we also have to be sure to control for other confounding factors. What this means is that when we set up an experiment, the only thing that's different between the experimental and the control group is the manipulated IV. So, of course, in the drug trial of Alzheimer's, the only thing that's different between these groups is the one group that's getting the real pill, the other group that's getting the fake pill. The one group doesn't sleep more, the one group doesn't live at a better nursing home, the one group doesn't get to see family and the other group doesn't. Those could all be confounds. Those have to all be the same between both groups. The only thing that's different is the manipulated independent variable. So once again, a quick review here. Descriptive research, we just sit back and observe and record. Correlations, now we're putting numbers to things, but we're not really controlling how it's measured. We're just measuring, putting numbers, and then calculating the correlation coefficient. Finally, if we want to say something causes another, that's where we do the experiment. It's a big pain in the butt. It takes a lot more time and effort, but it's valuable because knowing whether something causes another thing is worth the effort. So, how do we think about psychological, medical, or much research in general? First of all, we want to know what is the IV. So, for example, I've seen the alcohol consumption. There's a lot of studies out there saying moderate alcohol consumption can cause lowered hypertension, for example. And oftentimes that cause-effect relationship sounds interesting. We stop there. But what the headlines also don't tell us is what was the sample. So that means we have to think critically, actually maybe look up some of these studies if we want to use that information to make decisions about our lives. Because if that cool finding was not done on a sample for my population that I'm in, that's all it is for me. It's interesting, but it doesn't affect me. Quick review. What do we use to predict? That is a correlation. And of course, explanation in terms of saying what causes what. That's when we do experiments. So Mary was deceived by a boyfriend and says that all men can't be trusted. What is her error? She should realize that a sample of one is not a representative sample. Maybe if Mary had dated 100 boyfriends and most of them were deceitful, that might be a little bit more representative, and I might be able to go along a little bit more with her generalization. Which would an experiment be more useful than a correlation for? If we're doing an experiment, the whole point behind all that work is because we're trying to explore this idea of causation. So that one word gives away the answer here. Here we see a clear hypothesis. So we're saying one variable, smoking marijuana more than 5 times a week, is related to short-term memory deficits. That means they go together positive. Positive correlation we're hypothesizing. The more marijuana you smoke, the more short-term memory deficits you're going to have. And of course, I gave this away a bit. This is a good example of a well-worded hypothesis. Maybe the theory is that marijuana smoking is bad for your memory. Let's do a quick fill in the blank. Research participants have an equal chance of being selected to either the experimental or the control group. This is bringing in our idea of random assignment. You're either randomly assigned to the experimental or the control. It's not the women in one group, the men in the other, the old people in one, the young people in the other. Those would be confounds. those should balance out between the groups if they're truly randomly assigned. Similar concept is everyone in the population has the same chance to be in the sample. That is random sampling. Similar concepts, but not exactly the same. This is just to give you an estimate of not only is a correlation there or not, but how big is it? Correlation of 0.78 would be large. Correlation, on the other hand, of maybe 0.2 would be small. Which one would give you better prediction? 0.78. And if we looked at the scatter plot, a 0.78, those individual data points would be much more grouped around a central line. What is controlling what people are exposed to? This is the manipulation. And of course, we manipulate what? The independent variable. Related to this, what is manipulated in a simple experiment? It is one independent variable. Now, you can have more complicated experiments where you're manipulating multiple variables, but for our purpose, there only is one variable that's manipulated in a basic experiment. Let's test critical thinking here. Study shows that everybody in the control group, experimental group, feels better after a month of therapy. Does this prove that the therapy worked, that the therapy causes better health outcomes? The answer is no, because it's not just enough to show that people feel better after taking a pill or getting a certain kind of therapy. You need to show in an experiment that they feel better or show more improvement than the control group did. And again, this is because, due to the placebo effect, people who spend their time or spend their money on any kind of therapy are on average going to think that it works. To show that it really works beyond just the placebo effect, you have to show that the improvement is more than just placebo. Quick true and false. This is true. Basically an explanation for how something or some phenomena in the world works. Is thinking critically, saying it happened to me, so that's the way it happens for everyone? No. Again, representative samples, a sample of one, does not generalize very well to large samples or large populations. This correlational data allow us to assess cause-effect relationships. By now, that answer should be an emphatic no, false. Can there only be two variables involved in a correlational or experimental study? That is false. We're talking about the basic kinds. You can have certain kind of correlations between two variables that are adjusted for the effects of many other variables at the same time. But let's keep it simple for our purposes. But I just want to let you know that if you read some studies, you're going to see more than just two variables in a correlational study. Just a fun example of a finding that many believe to be true, that there's absolutely no research supporting that I could find. Also, basketball players having a hot hand. Is this true? There's been lots and lots of debate about this, especially in NBA circles, but the research shows that it's not, if there is any evidence, it's very, very minimal. Making a shot is sort of like flipping a coin. Sometimes when you flip a coin, just like shooting, you might get heads 10 times in a row. It might really feel like sort of like playing blackjack. You've won 10 hands in a row. That does not mean that you're any more or less likely to win the next hand. So a quick example of using research to something that I think is interesting. Here is looking at intercessory prayer. Basically, people, they do a nice job of saying the population they care about, coronary care patients, and they get a sample, not surprisingly, from a coronary care unit. And basically they're saying that the experimental group had people praying for them without their knowledge. The control group did not have people praying for them at all. What's nice is this is a good example of research saying that before we started, we did some tests to show that there were no statistical differences. So before the experiment, the experimental and the control groups seemed to be exactly the same. Now, after the prayer period, we see control patients required more ventilatory assistance, more antibiotics, and more diuretics. So this data seems to show that even though if people don't know they're being prayed for, they seem to have better health outcomes. Now, one thing I would like to know, sure, these things are significant, but how big is the effect? Were the people who were prayed for able to go completely off antibiotics or almost completely? It doesn't say here. So once we know there's an effect, which there seems to be in this study, we also want to know how big is it. The next important thing to consider is, has it been replicated? Many other studies have tried to replicate this. Some have slightly replicated it, some have not. So when we consider this effect of people being prayed for and not even knowing about it, if there is an effect, I'm fairly certain to say that the effect is very small. But what do we know about spiritual interventions in healthcare? This study I thought was interesting because it's a newer, more updated version. Also doing what's called a meta-analysis. It's taking a bunch of individual studies and sort of testing the replication effect in one number and in one study. What's interesting with this one is that they specifically excluded the intercessory prayer or distance healing that we talked about in the previous study. But also what they found out was there were a lot of significant effects of incorporating religious and spiritual interventions in mental health care, right? So different than the coronary care population we talked about on the previous slide. Depressive symptoms look better. Now, also decreased stress, alcoholism, and depression for those in this religious spiritual intervention group. The problem is, again, we know that these effects are significant, but they don't say how big they are. And when I looked at the study, I couldn't find a good table showing the size of the effects. So of course, if I was a clinician, a psychiatrist, a clinical psychologist, I would be saying, this looks interesting, but since I don't know how big the effects are, I'm guessing they're probably small compared to a lot of the other effects that I need. So for example, with a mental health care group, something that's going to have a big effect is, have they been abusing drugs? So before I even consider this religious and spiritual intervention, I want to make sure that the people in my critical mental health care unit are clean and off drugs. And then maybe we can try some of these smaller, still helpful, but smaller interventions. So thanks for hanging in this long. I apologize that this is reaching about an hour, but I think it's really important to lay a foundation for understanding psychology to be able to dig into following topics the rest of the semester that we'll cover. So I hope you found some interesting things to discuss on the discussion boards. I'd like to see, how has research affected your life? How might you look at some things that you're interested in from a research perspective or through a research lens? How might you design a study? How might you measure certain variables to put into a correlation? So lots of ways you could go to discuss this, but take a stand, step in, and let's see what you have to say about research in psychology.